Hello everyone and welcome to Lab 4, Magnetic Braking with Faraday. As a little bit of an introduction, the purpose of this lab is to simulate the time-variant magnetic field through Faraday's law. We will also collect observational data of a magnet falling through a conductive tube of aluminum foil. Then model the magnet-tube interaction computationally. We will then compare our model to the predictions in our observed data. The results were that the simulation time was 0.279 seconds and the observation time was 0.268 seconds. So let's discuss a little bit of the physics principles that we will be using to create our computational model. First is a Biot-Savart law. This describes the magnetic field due to a constant electric current. Next is Faraday's law. This predicts how a magnetic field will interact with an electric circuit to produce an electromotive force. Third is Lenz's law. This describes a current induced in a circuit due to a change in magnetic field is directed to the opposite of the change in flux. Finally, we will use Newton's laws of kinematics, which will allow us to update velocity and position of an object when being manipulated by a force. Now let's discuss a little bit of how we applied that to the computational model. So first we inputted the length, width, and radius of the aluminum foil tube. We also inputted the mass of our bar magnet. We then created a function to calculate the dipole moment or the magnetic field due to a dipole. We also were able to calculate the change in flux over the change in time. And we were then able to use this in order to construct our computational model. These are our results. As you can see, we see the bar magnet flow through the aluminum tube. We also see our velocity versus time graph in the left, and the time in the tube in seconds, according to the computational model, was 0.279 seconds. The intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current and which from counterclockwise? Counterclockwise is represented by the red, and clockwise is represented by the blue. We can tell this through Lenz's law. What happens to the dynamics of the system when you flip the magnet around? Our current flow would be opposite to what is present now. How does the total time in tube of your real-world system compare to that of your computational model? How might the computational system be made more accurate? My time for the real life was slightly slower than that of the computational model. We may be able to more accurately predict this by ensuring that we account for environmental factors such as the cardboard within the aluminum tube, along with air resistance, and more. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Well, as you can see, the velocity versus time is actually, the velocity is still increasing, even though it is increasing at a slower down rate, continuing throughout the graph. This displays that there is a force counteracting the downward motion. However, though, it is not enough to prevent the magnet from falling to the floor. In conclusion, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Well, if we were to reduce the resistivity to zero, the magnet would actually remain inside the aluminum foil. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, we would no longer have complete rings to calculate within our model. So we would have to modify the way that we quantify our model in order to account for the lack of complete circles. Thank you so much.